So let's look at the structure of the Earth. And the Earth is really defined by four main layers: the crust, the mantle, the inner core, and the outer core. And this picture gives you an idea of each of those layers and how they make up the inside of the Earth. And let's look at those layers in a little more detail. The first layer, the crust, it really is the rigid outer layer that makes up the continents and the sea floors. So really, any area that we touch, whether it's ocean or land, top of the mountain, all of that is the crust. And the crust, you can see in the picture there, is about 0 to 100 kilometers down from the surface of the Earth. If we were to look at the crust, the ocean floor, though it's very thin in the crust, it's actually quite dense. If we were to take a sample of the ocean floor, send a drill down, we would see that it's much more dense than a continent, which is much thicker and less dense, and that's why that continental land is up above the ocean floor. It is less dense, has a tendency to rise up and come above the surface. The less dense continent and the more dense but much thinner ocean floor. When we look at the crust is actually made up of two separate layers. And the first layer is what's called the lithosphere. And the lithosphere is really just this top portion, the crust and the upper part of the mantle. Just the upper part of the mantle and the crust together is the lithosphere. As we go our way down into the mantle, this is where we get to the asthenosphere. And the asthenosphere is the area in the mantle down below the lithosphere, down in there, and it is this fluid-like mantle. Fluid-like. It is still a solid, but it is almost like a melted plastic, where it's got this fluidity to it, and that's between the lithosphere and the core. And the core is really the center of the Earth, the two distinct layers in the center. First, we have a liquid outer core. And you can see the liquid outer core at about 2,900 kilometers down. We get this liquid outer core. And as we go deeper towards the center of the Earth, we get eventually down to this solid inner core. Inner core solid, outer core is liquid. We know these properties of the Earth not by digging down, though, and that's the important thing. We can't just send a drill down to the center of the Earth. What we have to do is actually analyze the structure of the Earth using different methods and collecting evidence. And scientists have actually obtained evidence about the structure of the Earth both through direct and indirect observations. And a direct observation is really just taking rock, analyzing it. Whether it's analyzing rock on the surface or going to a volcano and getting rock from inside the Earth, the interior, analyzing that rock directly. And that's called a direct observation. We may also actually use indirect observations, so using tools to measure things such as gravitational force. And we can use equipment to determine that different parts of the Earth have different gravitational forces. And if that's the case, they must have different densities. So if we go to a different place on Earth with a different gravitational force, that means below your feet, inside the Earth, is much denser. And so we can use these indirect observations. We can't actually touch that dense material, but we can measure it. We may also use modern technology, things like GPS or infrared or radar. These allow us to actually see parts of the Earth that we can't see at the surface. It allows us to go deep down into the surface using technology and getting some indirect observations. That's how we know the Earth is the way it is, through these indirect observations, looking down deep in the Earth using our scientific tools. Well, the Earth is actually quite dynamic. It is constantly in movement. And we are aware of this on the West Coast, where we get earthquakes, this constant movement of the Earth. But we were not always aware of this, and we couldn't always explain it. It first was proposed by Alfred Wegener, a German, that the continents have actually been moving on Earth. these continents have slowly been moving around. And Wagner called it his theory of continental drift. And this idea really came from looking at maps and looking at the shapes of the continents. And if we look at a map, whether it's a globe or a map of the Earth, we can see that if we put all the continents together, cut them out much like a puzzle, they kind of fit together. They can form this unique single continent shape. Now, Wagner was not the first to propose this idea of using puzzle pieces. What he was he was the first to actually start to look at other evidence. Wagner started looking at both fossil and geological evidence to support this continental drift theory. And some of this evidence is like in this picture here. In terms of glacial evidence, what Wagner saw was that if we looked at the glacial evidence that exists right now, there's glacial remains in South America, and in Africa, and in India, and in Australia, and all of Antarctica. Glacial remains. Now, if we look at this glacial evidence, if the Earth was in one place, as it is now, the equator goes right here. How is it possible to get glacial evidence way up here north of the equator, and it magically stops in South America but goes in Africa and doesn't take up all of Australia? And how Wagner explained it was that the only way this is possible is if these continents were all together on the South Pole. Also, some fossil evidence. Fossil evidence that exists on the eastern part of North America and the northwestern part of Europe and Asia. Fossils that obviously could not just get across the water. And why would they appear here and here? Well, his explanation, if those two pieces were together, then those fossil remains would have this north-south pattern, much like a migration pattern, going from one part to the other. Those continents would have been together, connected. And Wagner was the first to use this evidence. And he proposed that at one point there was a giant landmass, all the continents together, in a landmass that he called Pangaea. This giant supercontinent. Unfortunately for Wagner, he actually died before his theory was accepted, because in Wagner's time there was no explanation for how. He didn't know how this worked, he just proposed that this must be the case. Now, it's not just these fossil remains. Wagner looked at a number of fossil remains. And if we look at this picture, look at some of the fossils of reptiles that exist in different parts of the world. There is this land reptile where evidence exists in South America and in Africa. Well, how is that possible unless they were connected? Also, fossilized remains from plants that follow a pattern through multiple continents. And again, how is it possible unless they were connected? Well, let's look down here at this freshwater reptile. And this is probably one of the most important pieces of evidence. Freshwater reptile. Freshwater meaning if it's in South America and the southern part of Africa, how could it have existed in those two places? It obviously can't get across the saltwater ocean, and the only explanation is the continents must have been together. This idea of one supercontinent, one Pangaea, was Wagner's theory, but again, how the continents moved was unknown at the time, and we're going to get into that more as we look deeper into this section.